hand we were dealt. Our project was getting a robot to be controlled while wearing an armband. My name is Austin Pemberton, and I was the project manager for the project.
My name is Alan Navarre Picard, and I'm the project designer.
It's Mike Dyer, programming, testing, and verification.
My name's Ethan Hickman. I was a component designer for this project.
My name's Caleb Thompson. I was over the documentation, just where I was needed.
And this is a short video kind of giving an overview of what the robot looks like and functionality.
The field of robotics consists of electromechanical devices and machines that can perform a variety of tasks and applications. The inspiration for this project came from the thought of a person not being able to use their fingers to control the robot due to either the inability to use their fingers or just a handicapped person.
So the main project objectives for this was to get a robot to actually receive and then carry out the objective as far as once it receives the signal from the EMG signals from the forearm, then it can sit there and go and do whatever the signal that it was given to do. And it was also to use modern technology, production technologies like CNC and 3D printing.
So the model.
One slide, Mike.
Yeah,
Should
I
be
think
budget.
yeah, there we go.
So the overall budget we were given was $1,000. We ended up coming in about $250 under budget. A couple of the things that we did kind of end up spending twice on. One was the battery pack for the external touch screen. First one we had was kind of a cheaper setup, and then we ended up going with one where it was basically like a battery pack to sit there and recharge your cell phone or any other battery device. And then also the camera on it, the ribbon cable that came with the camera ended up being a little too short, so we ended up having to buy another one that was longer so that we could get the camera to mount where we needed it to.
Okay. So the Maya armband was ideal for a project because of the fact that it allows the user to control movement precisely without actual physical connection to the robot. This is accomplished through taking EMG signals from the forearm and also using things like accelerometer. Along with the Meyer Armband, we use a wireless touchscreen interface device. This serves as a video feed as well as being the backup controller and communication hub between the armband and the robot. Some components of the robot include an infrared camera, a Raspberry Pi controller, and a power distribution board. The peak power consumption is 6 to 8 watts. So the motors chosen for this project are brushed DC motors. These were used due to their cost effectiveness and a power weight ratio. The rated current for these motors are 1 amp each per motor, and they have a motor torque, a max torque, of 0.49 Newton meters. Next.
We chose to use an omnidirectional wheel for this robot. One, they still move like a normal wheel, entire setup, but it also gave us the ability to have a zero turn capability. Also, with this design, we do not have to design any steering linkage that could overcomplicate things or be a source of failure should a piece of steering linkage break. And we chose to use aluminum for it is easy machinability and to help keep the footprint down. Most of the holes that could be slotted, we slotted so that it would make assembly easier and for any tolerance issues during the machining process.
We're using two basic technologies to communicate between the robot and its peripherals, Bluetooth and Wi-Fi. The first Bluetooth is used by the EMG, the Myo Armband, to enable it as a IO device. As first glance, the Myo Armband is solely a machine input device. However, it does act as a input device to the operator as well because it provides haptic feedback that can be triggered by the robot controller itself. The robot Pi actually broadcasts its own Wi-Fi network that acts as a wireless access point that other devices can connect to, namely like the handheld touchscreen controller. The controllers that we actually went with are the latest generation Raspberry Pi, Model 4Bs. They have a CPU clock speed of 1.5 gigahertz and 4 gigs of RAM. And since the Raspberry itself, the operating system that you run on them, is a Linux distribution, we were able to take advantage of running secure shells, SSH terminals, from the handheld to the robot itself. That way we wouldn't have to connect extra peripherals to the robot like a mouse, a keyboard, a full-size display, so on and so forth. To power the system, the handheld itself just uses a 5-volt battery power supply, just like what you would use with a on-the-go cell phone charger. It has two 18650 style batteries that can be swapped out, on the go if continued use is needed. The robot had a few other considerations as far as power goes. It needed the 5-volt control power for the Pi and its peripherals, as well as a 12-volt supply for the motors themselves. Our solution was to take a single 12-volt battery. That battery will connect to our first stage of power distribution. And in this first stage, there are two sections in parallel. One side has a 12-volt to 5-volt converter that feeds the Pi and its peripherals, and the other side, the 12 volts, goes directly to the motor drive board, as seen in the picture here. The other main peripheral that we added was a robot-mounted camera. It's installed and allows, from the handheld touchscreen, as long as it's connected to the access point, to watch in real time with minimal lag, first-person view of the robot's surroundings.
So with this wiring diagram, we were very challenged with it because this wiring diagram we actually designed before we purchased any of the components for the robot itself. First and foremost, I myself had never had any prior experience with Microsoft Visio or any other wiring diagram software for that matter. So there was a great learning curve when it came to this. But the bigger challenge was, as the designer, was, I had to make sure that all of these components would indeed go together before we purchased them, so that we weren't purchasing items and then being not able to use them.
So here is a list of the components that were actually drawing power from the battery. The biggest one, of course, being the actual drive motors, and with 4 of them, gave us an overall power consumed wattage of about 48 watts. The power distribution board itself can distribute about 20 watts of power, and that's where the Raspberry Pi, camera, and all of the other 5 volt sources were getting their power from. So with the total wattage being about 68 watts, we were then able to start calculating what size battery requirements we needed. And for the main thing was, if we had the actual in face or face-to-face presentation, we needed it to at least last, roughly an hour and everything. And then the biggest batteries, or the biggest voltage that we had, was for the motors themselves, being 12 volts. So with that being said, we were able to calculate the main battery capacity of 18,000 milliamp hours.
Here are the main components that could possibly wear out or have issues with during the life of the robot. The Myo Armband is pretty robust and high quality part that was sourced with good reviews. That is why it scored so low on the scale, whereas the battery is a lower quality lithium-ion battery, and if something goes wrong, it could have the potential of catching fire. Plus, it is the main and only source of power for the robot, so if anything goes wrong and it does not supply power anymore, then the robot will stop working. That is why it scores so high.
Here's a basic program overview, our program flow, a pseudocode, if you will. From initial startup, of course, program initialization. Before anything runs, it checks to see if any controller is paired. If not, it just sits in a continual loop till it is. Once the Myo Armband controller is paired and a start command is given, the program will actually begin. Whereas there are 5 basic commands from the operator to the robot: forward, reverse, turn left, turn right, stop. Depending on which command is given, the controller will send output to the actual motor hat and give that command. Whereas certain drive parameters are able to be changed from the terminal, such as motor speed. At first initialization, starting this up, we set all the motors to the same speed. However, coming directly from the factory, at price point that we spent on these motors, they didn't all have the exact same RPM actual real world output. So, we had to actually change the motor speed going to each motor just to keep it going.
Okay.
For this would be given to the end user. Of course, everything from starting with the fully charged battery, of course, to the SSID and password at the access point that they would need to connect to in order to open that secure shell to start program. As well as a special note how to actually access the real-time video feed from it and what to expect as as the program runs, and just to make sure that that haptic feedback to the operator, they understand what that means, so on and so forth. There again, 4 basic commands, 5 actually. The move forward, finger spread, move right, move left, fist, move backwards. And of course, resting would be just, no command at all, given a basic stop.
And for the overall timeline, the project was done over a 2-semester period. The first semester was just coming up with the initial idea, concept, and then figuring out a list of components that we were going to need and getting all of the design details figured out. And then at the end of the first semester, we sat there and turned in a purchase order for all of the parts and stuff that we were going to need. So that way, when we came back from break in January, we could go ahead and start doing the assembly part of it, get all of the Raspberry Pi stuff together so that Mike could start programming, since that was going to be a big chunk of the time that was going to be spent on it. And then we were planning on, we had everything finished or to a good point at spring break, and then coming back from spring break, we're going to sit there and put all the finishing touches on it, but kind of got thrown a curveball with all of the COVID-19 stuff and everything that has happened since then. So.
So with the overall design of the project, us being the first graduating class of the Mechatronics program at UTC, we wanted to not only make a project, but make a project that other generations could actually build upon if they wanted to. Being that the robot is extremely modular, means that it is very, very easily capable of being customized in several different ways for basically any application that any other students could possibly think of, whether it be other sensor placement or even another means of modularity for it, it being mobile. With the initial design, there were some aspects of the project that we were not able to get into this project. One being obstacle avoidance functionality for the robot, and then have a return to home or a dead man fail-safe functionality of the robot itself.
This again. Let's see.
Can you explain what we're seeing, Mike?
Yeah, so we're actually powering up the robot right now. And the robot Pi itself is booting up. It's using a computer monitor to simulate the handheld. And it's running that secure shell terminal and giving feedback as well from the terminal. Wave out, wave in, turn left, turn right, fist. The reason I like that feedback from the terminal is the armband itself has to be calibrated to the user, because everybody's EMG signals can be a little different. So, you know, if you're making a fist, but it's reading a wave in or a wave out or, you know, another signal, then, you know, it just makes it easier for the operator to be able to troubleshoot, you know, erroneous readings.
Mm-hmm.
Of course, the dog was very integral in a testing process. Let's see. Yeah. All right, so
Do we have any questions from any of the attendees today?
Yeah, thank you so much, gentlemen. It's actually did great work, and I have to mention something that they were actually ahead of the schedule. This team actually finished sometime before the spring break, but they just had to basically do some little changes in the programming, but everything was finished actually before the spring break. So before the COVID-19 thing started, and you know, and so it was very good from them, and so that's why actually we were able to see they completed the project. Thank you so much, gentlemen. I appreciate very much your hard work, and I will actually let the invitees to see if anyone has any question.
Sir.
Yes, sir.
H-Lead, this is Paul. Was just curious, if I can understand it, the wireless touchscreen, was that a receiver, or is that a separate control device? I didn't quite get the concept of that. Is it like the Armband, is that the only controller that goes to the robot, or is that other touchscreen also an input device, or is that a receiver?
Yeah. Actually, there's multiple input devices, but I will leave it for the team to answer you.
Sure.
I'll take this one if that's fine. So the touchscreen device itself has its own Raspberry Pi mounted to it, which is controlled by. And so what distinguishes it from the Myo Armband is the Myo Armband is essentially just a human-machine interface of sorts, like a input. Whereas the touchscreen itself is able to actually communicate and independently call and run programs, make parameter changes, you know, to the programs that are actually running on the.
And what about the video, Mike? I'm sorry to interrupt you. What about the video from the camera? Does the touchscreen, can you see the video from on the touchscreen, or you can't?
Yes, of course. Really, any device, even your cell phone, which is one of the things I was going to show.
In real time, of course, right? In real
demonstration time. Was, you know, in person, was you're actually able to connect any device to the access point and just go to its own web page that is broadcasting and see the real-time video feed as you go. So it's not just, it can make you know, give actual like course guidance. It can make process changes, parameter changes. But more than anything, what we used it for was a way to access the robot's internals, its programmings, without having to,
okay.
You know, have it, you know, the
do you guys have who has the robot at the moment? Can you just like show it to the camera if you don't mind?
That's fine.
Okay. So as you see, so there's actually a screen also on the robot itself. There's a small screen.
Yes.
That's just for to see the program.
Yeah, and
right?
it
doesn't have any controllability.
Well, it does have touch input, but you know, it's a 3-inch touch screen, showing a full-size desktop environment. So you can, show just the terminal if that's all you want to look at. Something that I would suggest for, future projects if they want to build off this is, actual display of, telemetry data such as, power consumption, direction, battery life left, whatever other
What
information.
about emergency stops? Did you guys program any emergency stop anywhere? Or is there any push button for emergency stop just in case you lose control on the robot?
So at loss of connection to the My Armband, the motors do stop. They don't enter a rest state. They actually just go to a full stop.
Okay, I guess we can do that for we can improve on the future just to add some physical e-stop switch or button.
Right. And that's kind of what we were talking about in our future, ideas in this previous slide. This return to home dead man fail safe. In just like a robot teach pendant, you have that dead man switch. Way in the event, of operator incapacitance, your robot enters a safe state. If that makes sense.
All right, thank you. Any questions? Any other questions?
Yeah, actually, I got a quick question. I'm Omar Tantal from Malo College, Kelly's brother. Congratulations, guys, on your first open house mechatronics and open day and graduation project. My question is, I saw the screen now, the touch screen. Is it touch or you use as a stylus to go to do an input on the screen?
It's both. It comes with a stylus.
Okay, and I've seen also that you guys bought two Raspberry Pi, right?
Correct.
So the other one is used on the robot?
Yes, one Pi is mounted directly on the robot, and one is used in the touch screen.
Okay, I guess the question is, Mike. So do you have the separate touch screen, the separate control touch screen?
Yes. Let me show that.
Yeah, and this is Paul. I had a kind of similar question too regarding the Raspberry Pi. What was your criteria? Why you chose a Raspberry Pi versus some other type of controller?
I think
The camera,
Navar,
I guess. So.
I think Navar can answer this question. Actually, for the design part, we did discuss about that, and Navar, can you answer this question, please?
Yeah, could you repeat the question, please, sir?
Sure. Why a Raspberry Pi versus another one? Like Omar was saying, an Arduino. Was there an advantage to the Raspberry Pi, or is just something you're more familiar with?
Well, the reason why we chose to go with the Raspberry Pis is because Raspberry Pis have actually come a very long way since their first inception. This being the fourth iteration of the Raspberry Pi, basically the Raspberry Pi itself has become more or less a small computer. Just the abilities that the Raspberry Pi 4 has in processing speed and everything else puts it, in my opinion, far beyond anything an Arduino or anything like that could even try to, start to process and do. And that's kind of why we went with it. We wanted that versatility, that ability to be able to pretty much do whatever, we could with it and not actually hit those, the limits of the process controllers that we were using.
Thanks, Navar. So I think we should start now with the next presentation. But actually, also, so just to highlight what he said. Basically, the Raspberry Pi is a lot faster. So it's 1.5 gigahertz as they showed. The Arduino is only 10 megahertz. So there's a huge difference. It's like hundreds of magnitudes higher. And also, in addition to of course, the RAM. The RAM is significantly bigger for the. He said it's like a computer. Raspberry Pi is almost like a regular computer. Well, thank you so much, gentlemen. I just want to remind you all, if you can, there's I sent over the chat. There's a link to a form for a survey. It will help us a lot, actually. Actually, also for the program accreditation, it will help us. I will actually, we will appreciate it very much if you can fill out the survey for us. It will take about 2 to 3 minutes. Thanks so much, gentlemen.
Does Mike have that touch screen?
Yes, it's right here. So background's kind of, let me see here. There you go. So it's mounted directly on the back here. If you see that? Golly. And then.
Come on, Mike. Hold that thing, son.
All right. So it's just like a small 7-inch tablet with a Raspberry Pi actually running it. Golly. There.
All right.
Okay.
Thank you so much, gentlemen. I think we should, just to stay within the time, I will let the other group start now. So Noah is the team leader. Can you please
Whoever
start,
has
Noah?
control of the screen needs to let it. Yeah, there we go.
All yours, man.
I appreciate it, man. All right. Let's see. All right. That's weird. All right. Are we good to start?
Please.
All right. And hello, and thank you for joining our presentation today. My name is Noah Grigsby, and I am the project leader for this group.
Hi, my name is Garrett Chisnall.
Hi, I'm Guido Marcila.
And I'm Caleb Berry.
And this is our design of an amphibious mobile robot that's going to be controlled over a cellular data network. The main purpose being for geological research.
Excuse me. So this is basically our needs statement. So there are different types of unmanned vehicles. For example, there are unmanned underwater vehicles, which are referred to as UUVs. There are unmanned aerial vehicles, which are referred to as UAVs, or otherwise known as drones. And then there are unmanned surface vehicles. So sometimes with these different types of unmanned vehicles, there can be issues with controlling them. For example, with UUVs, there we go. Sorry about that, I'm trying to see this. So UUVs, a lot of times what can happen is because these do go under the water, this can make the tracking and control of them sometimes difficult. Then of course with the UAVs, which are the drones, these have to fly. And so a lot of times they can't, the payloads that they can carry are kind of minimal. And then of course they are very difficult to control in storms and that kind of weather. And then of course with USVs, which are surface vehicles, those usually sit on top of the water, but what can happen sometimes is a changing current, maybe a very strong current comes or a large wave that can, make the control of the surface vehicles difficult.
So our project objectives, we were told at the beginning of our making this robot, is to build a mobile robot with ground and water capabilities, and also to be able to control it through SIM. It must be weatherproof and waterproof, and the unit purpose of this robot was to carry a payload.
Yeah, so to kind of build off of what Caleb was just saying and to reiterate basically what our robot's going to be doing. As a group, our goal for this project was to build an amphibious unmanned surface robot that was capable of carrying a payload for geological research. Another key note that we wanted to be able to do with our robot was that we wanted it to be able to be controlled via SIM card and GPS modules. And we wanted to show some of the advantages of our robot versus other unmanned vehicles. We're going to be utilizing long-range communication via the SIM card through cellular communication. We're going to have amphibious functions of land and water capabilities. And we wanted to highlight that it will be durable in extreme weather conditions, so it has to be in that certain scenario.
So this is a very basic visual that's explaining the goals and objectives we're going to meet with our project next semester. On the right, you have a cell phone, and we're going to design an app to control the robot and give it commands. And this app will send signals through our phone to the cell phone tower, and then through that to a SIM card module that's located on the robot.
Yeah, so with this being our preliminary design presentation right here, we as a group decided we were going to do some background research to try and find another design that was going to be similar to ours. And so with this robot right here, it possesses the features that we were going to integrate or potentially going to integrate into our current robot that we are designing, such as the amphibious functions of land and water capabilities. And as you can see here, this robot is utilizing a leg and propeller system. We decided to go a slightly different route from that, which you guys will see later on in the presentation, but it is similar. Likewise to this robot, our robot will feature full aluminum construction and plastic components, and we will also be utilizing silicone and rubber gaskets to ensure waterproofness as well.
All right, so here's our project timeline. We did our first presentation on February 11th. Then we followed it up on March 4th, a little under a month. We went to a more detailed design presentation to Dr. Khalid on April 2nd. And today we're doing our final technical documentation. For the fall, it's subject to change. We plan to have our robot complete by September 11th and the robot programming complete by October 9th, which is pretty much more than halfway done, and then have the final robot testing done by November 27th. Here's just a visual of our timeline. In the red, you can kind of see where we had to reschedule some things due to all this craziness that's going on in the world right now.
So here we have our design overview. So we have some things that we would like to, we hope to be able to do with this project. Different various tasks. Main thing being capable of performing functions during storms and that sort of weather. We have obviously here a raft function that's going to be going around the robot that's going to help it float above water. We're going to be using mechanism wheels, and this is going to give us better mobility over different various terrains. And then we have attached paddle wheels, and this is going to help us in our water mobility. So obviously we have a method that we're using for waterproofing that we're going to be using to kind of seal up around the robot to keep our electrical components away from any kind of water that may get in. And then of course, we want to be able to control and monitor using the subscriber identity module with the GPS.
So here, the next few slides, you're going to see some of our preliminary CAD drawings that I came up with. This is the chassis, the main chassis with the mechanism wheels, and then some L brackets and some DC motors that will be waterproofed. There are some various holes and stuff for connecting different parts and mounting things to the chassis. This is a engineering drawing here of this first part of the CAD. It's got a top view, front view, side view, and an isometric view. And I've got everything in millimeters. Here on the left, you can see the paddle wheel attachments that'll mount onto the mechanism wheels for whenever it comes in contact with water. And then on the right is a preliminary idea for a flotational device, and then a dome on top that will be have some form of sealing to keep the electronics housed above the water and keep water from getting in. And here we have another mechanical drawing here showing the different views.
Here we have our parts list and specifications. As you can see, we have the total amount of watts and current, amps and voltage that we're going to be using. You also see the cost and the quantity of each part that we're going to be using. It came up roughly around $725.
Here's a visual of the actual robot kit we're going to use. This is just the chassis with the motors and the wheels. And here we have our power calculations that we did, and this is how we found out which battery we were going to use. So we took our total power that we've calculated so far, and then we took a service factor of 1.3, which we decided was a good moderate value that we discussed with Dr. Tantawi to account for errors that we may have not previously seen, and then we took that value and doubled it to avoid depleting the battery too quickly, and we want to keep the battery life as high as we can. We don't want to deplete it too quickly. And it's a 12-volt battery, so we took that, found the amperage, converted it to milliamp hours, and then we just went ahead and rounded up to 26,000.
Yeah, and so right here, we're going to dive into the basically nitty-gritty specifications of each of our components that we wanted to highlight that are going to be incorporated into our robot. Starting with one of the most critical components right here, we have our 4G or LTE GSM module. And one thing we wanted to highlight here was that it is a quad band LTE module, so it will allow us to utilize the fastest cellular networks possible. Specifically, we're going to decide to go with T-Mobile or AT&T. We have not specifically chosen which one yet. Another thing we wanted to highlight was that the operating systems listed below range from Microsoft, Windows, Mac, and all the way to mobile device, which is the purpose of our project will be used with the mobile device. And that way, whatever the customer wants, they can use it through any sort of interface that they want.
Here we have our Raspberry Pi 4, and as stated in the previous group, we decided on the 4 because it is a little bit faster than the, say, like Arduino and things like that, with a 1.4 gigahertz 64-bit quad-core processor. So basically, this is going to be kind of the brains behind the robot. This is where we will put our program, and this is what will control most of the aspects of our project. Here we have the powers with using the CanaKit 2.5 amp micro USB.
And as you can see right here, bouncing off of what Noah had said earlier about our battery, here's the battery that we decided to go with. It is a lithium-ion battery, and it is a 12-volt battery, as Noah had said. The capacity is 26,000 milliamp hours, as we calculated earlier, which should give us ample amount of time in the field to perform the various functions that our robot is designed to do.
Here we have our power converter. Most of the time we will be sending 12 volts to our DC motors, but in the case where we need to have that power, say to power up the Raspberry Pi and some of the other components that run off of 5 volts, we have this power converter here that we're going to be using to take that 12 volts down to 5 volts to power up those other components.
So to build off of that, this component right here is our power management board, and its main purpose, as it's stated in its title, is to manage most of the power that is going to be going through our robot right here. And we wanted to highlight the fact that we have labeled right here that all of the pin functions right here, which will give us an ease of access later on in our fall semester when we do go to assemble it, so that we won't be confused or anything like that. And another thing we wanted to highlight about this is that this does give us the function to have a safe startup and shutdown in the event that we do encounter any difficulties in the field, so that we don't have a failure of our robot.
Here we have our motor drive, and this is what's going to be sending power to the from the battery to the DC motors. The thing to note here is the H bridge. This is going to allow us to have have our wheels be able to be bidirectional going forwards and backwards. And then, of course, in the case where we want to say maybe slow down for any reason, we can go from the 12 volts down to the 5 volts using the using pulse width modulation.
And here, right here, you guys can see that we have our DC motors, and as stated previously, we will be supplying these with 12 volts, so we will be able to maximize the torque rating right there of 0.88 Newton meters, and we also will be able to utilize its full potential as far as speed goes. This will be plenty, as we calculated earlier, to accommodate for any sort of payload or anything that we will be accommodating with our robot.
Here we have our robot kit. So noting here the dimensions, it's 260 millimeters by 240 millimeters by 8 millimeters, which putting that into US terms, that's coming out to roughly around a foot by a foot. Another thing to note is the payload weight coming around 20 kilograms.
And the last component, but certainly not least, is going to be our camera. And as a group, with the hope of this camera right here, as Noah had said earlier, we're going to develop an app to control our robot right here. And so the hopes of this camera is that it's going to be able to give us a live video feed as the robot traverses through a certain terrain, and in the event that it has to traverse over an obstacle and even be able to see in water, this is going to give us the capability to do so. And also it will allow us to, whenever it comes back to the user, to pull information from and be able to use it for documentation purposes.
Here we have our preliminary wiring diagram. It's pretty similar to the previous groups, but one thing to note that's different is our SIM card module. Other things to note is our 12-volt power supply, and that'll send voltage into a converter, and which will let 12 volts out to the motor drive, and then 5 volts to the power distribution board, which will let the power go to most of the other components throughout the system.
So here's just a visual of our budget sheet. The main difference in this budget sheet is that we added miscellaneous parts. It comes up to roughly an extra $100.
And then, of course, it is the group's hope in designing this amphibious robot that we are able to achieve the following goals, and I think we've got the tools necessary to do so. Obviously, the goals being that we want to be able to communicate and monitor the robot using the SIM technology. Another important aspect that we hope to achieve is the ability to carry the payload for the geological research. And then, of course, because we are using this robot in and out of water, we have to make sure that it is waterproof and weather resistant in different various storms and things like that.
Any questions?
Thank you so much, gentlemen. If you don't mind, can you go back to the budget sheet, please?
Yes.
So I just want to see where's the total price, the total cost.
It is.
Your screen
right
may be cutting it off because on
here.
mine it's cutting off.
Okay, I
on the
see.
bottom.
It's
Yeah.
800. Okay.
Mine's cut off
Yeah,
too.
there it is.
Of which there's 165 for the battery. The 26,000 milliamp hour batteries is 165.
Yeah.
Okay.
Mm-hmm. Yep.
All right.
Hey, this is Paul again. My only question that I was thinking about is that they mentioned about the possibility of including a fail-safe or device or able to shut down. Since this is supposed to be like a waterproofed or underwater, well, not underwater, but this is like a boat. Correct?
Yeah, it's a raft that's able to propel about like it on the surface of the water. So the paddle wheels on the omnidirectional wheels, the wheels will be partially submerged, so that'll allow it to propel in different directions.
Okay, so is there a possibility of this once it gets like halfway across the lake or the river that it would shut down, and how would you retrieve it, or what's the chances of that happening? What's your solution for that possibility?
Let's see. That's a good thought. A potential, I guess, a first solution would be to try to make sure we've accurately measured the capacity of our battery and consistently get it to run within an hour so that we can time it. And in the event that it shut down, like in the middle of a creek or river, the SIM card module that we have has a GPS module, which will allow us to locate it wherever it's at through coordinates. So if it shut down while it was like, let's say a few miles away and we couldn't get to it immediately, we'd be able to track it. And then I guess we'd have to develop a method of retrieval, maybe getting a boat or something. Yeah, but we'd be able to find it if it shut down in the middle of a river or creek, something like that.
Yeah, I have to mention actually the batteries actually is very dense. The 26,000 milliamp hours actually is a very dense battery, and so it's actually it will probably last a lot longer than an hour. But just in case the battery actually goes down, or I mean, I think it's actually a good thing to think about, so that it doesn't get lost. Probably we should program it so that it shuts down the wheels, so it doesn't consume battery power, and just concentrate the battery power all on the GPS the SIM card module basically, so that you can locate the GPS. I think that's a very good actually thing to think about.
Thank you.
Thank you.
Another way around it may be to monitor the battery capacity, and you could put code in there that if you get down to 55%, that it returns to start regardless of what operator inputs go, just to ensure that it always gets home.
Well, okay, like a
That's a good
return
thought.
home feature. That's
very good. That's a very good point to point out. And, you know, with the hopes that once we do create this app, that we will have full ability to monitor each component on our robot, specifically the battery, like you pointed out. And that's a good point to make, is that once it reaches a certain percentage, likewise the other group, that we'll be able to develop some sort of fail-safe return home feature. So yeah, thank you for that input.
Thank you, Mr. Arlington.
One other thing that I noticed, it had a good sized cooling fan on the power unit, and your original or your proposed drawing shows a nice smooth sphere over the top. So assuming that these 4 drive motors are going to consume a lot of power, that processor may get hot. So you may want to put more thought into the airflow of how air can get into your sphere, not drown, not allow water in, but let air come in and have a way to exhaust so that your board is being cooled properly, but you don't defeat your goal of having it waterproof, you know, so if it started raining.
Exactly. Very good
still
point.
be alive.
Okay.
That's
Okay.
actually what Wayne is mentioning is something similar to, you know, the electronics that they use for space applications. You know, in space there's no air actually, and so when the electronics heat up, what they do, they use a lot of you know, metal, you know, heat sinks. You know.
Okay.
So actually, you might need to go to that route. Actually, you might need to extend heat sinks up above the, you know, the dome, or Wayne said, find some way to allow air in without having, you know, without allowing water in.
Okay.
Something to think about, actually.
Yeah. Okay.
That's a great thought. Thank you.
Thanks. So this Stephanie, I don't know, is Stephanie? Stephanie, are you with us?
Yeah, I'm here.
Yeah. So this project actually was. So actually, originally, Stephanie, Dr. Stephanie DeVries is in the Department of Geology, and she was looking for actually a robot that basically takes water samples. So this is what the project is intended for initially. But what we decided to do, we actually wanted something that is, let's say, multi-purpose. So in other words, it will be designed such that it will take a payload to do water sampling, or for example, a probe, you know, a sensor, pH sensor or temperature sensor, or whatever, or a camera, for example, for underwater and so on. So it's basically a multi-purpose. So I just wanted to mention that point. Do you have any questions, Stephanie?
I'm a little
Any
curious.
comments?
Well, it's very different than I was imagining.
Okay.
I'm curious, like, about how, like, if you've thought through like the collection process, like how are you going to collect the payload?
Yeah. So for that part, for the payload itself, basically, we're gonna have another group work on it. So they're just gonna design the delivery system, the robot, and then for the payload inside that, we'll do the collecting. That's gonna be for another group's project.
Okay. Now, so is this like the locomotion on this then, is it intended to basically drive along sort of a dry bottom, but then if it comes into contact with water, it'll float on the surface and you can just navigate around on the surface of the water?
Yes.
That's correct.
Is that the idea? So the idea is it should never actually be submerged.
Right. Correct.
Right. Okay.
Yeah, the device, the robot shouldn't be submerged, but depending on which payload you have equipped to it, that could be submersible, depending on how it's designed by the next group.
Okay.
And the reason we're going to achieve a lot of mobility, like even when it gets in the water, it'll still be able to turn and go forward and backward because we're using 4 different motors. So we have 4-wheel drive and they're bi-directional. So even though there's no like steering, we achieve that with alternating the motor directions.
So what kind of, do you have any sense of, like I can see in like a relatively still water body, say a lake or something like that, where there's a lot of application here where you can steer it around and take like aerial samples at the surface to see how spatial chemistry changes, for example. But if you're talking about a river with a current, do you have any sense of what the maximum current would be that this would be able to withstand before it would overcome the locomotion capabilities of the robot?
Not currently. That would probably be better discovered through testing. We kind of have to come up with some kind of, we've come up with a final design here, but I think that would kind of depend on if we design other different like land to water features for like the wheels. Like if we, instead of doing a paddle system, if we changed it, if we gave it its own propellers or something, it kind of, I guess that'd have to be achieved through testing.
I think for the case of a stream, if there's a strong stream or a river, in that case you can just actually mount something. You can just mount something, or have the robot connected to something so that it doesn't move. It stays stationary. I think that would be possible.
Yeah, tethering it
That
to
does not,
something.
if that doesn't change doesn't affect the research that you were doing, Stephanie.
Sure. No, I was just more thinking about like, the applications. That's all. And I was concerned that, I mean, if you like the way it's designed, I can, I think if you focus on the current design as being applicable to like low current situations, I would pick one or the other, basically, because I don't think that, I don't think it's, because in a stream situation, you're really going to have to consider the like sort of hydrodynamics as well, because you could, even in an hour, you can have like up to, flash flooding, you can have water can rise a foot or two in a pretty short period of time. And if you have something kind of blocky and round like that, it's just going to, so even if it was tethered, it would have a tendency to not stand up well to those currents. So
yeah.
So I think it's great, like in terms of like, for example, like I said, a lake or a still water body or something like that, or a very shallow stream or a very slow moving currents. I can see where we can go forward with this.
Okay.
Cool. Great. Thank you.
Thank you.
I got a quick question. What is the weight of the robot on ground and when it's submerged? Like, well, you probably mentioned that on one of your slides, but what would be the weight of the robot with everything on it?
We're not entirely sure yet. We know the weights of certain components, but we haven't actually assembled it and weighed the entire thing. I don't know how much these little circuit boards weigh, but like where was it? We know that the main chassis with the motors and wheels, which is probably going to be the heaviest piece, is about 2.1 kilograms. So maybe close to 5-ish pounds. But like I know the raft looked big, but obviously it's going to be full of air, so it's not going to weigh that much. And we'll probably make it, or if we use foam, then it'd still be light. But I don't know. I didn't calculate the weight of the battery. The battery is going to be heavier because it's bigger than a lot of other kinds of batteries used. Like it's bigger than an 18,000 milliamp hour battery.
Yeah, but it's actually a lot more expensive. It's the battery that the other team used. I think it was like $40. It's $165, right?
Yeah, and I kept trying to find a cheaper one, but like I could only find.
That's not a problem, but I think it should be dense. It should be just like phone batteries. It's very dense and compact.
Yeah, but I'm not entirely sure of land or water weight, but that'll definitely be calculated once we assemble the entire thing.
Well, thank you so much, gentlemen. I think we should end. We have only 1 minute left, so I don't know if any other comments or questions.
Yeah, I have one.
So, yeah.
Yeah, this is I can. So just.
Yeah, I can. Yeah.
Yeah.
Dr. Kaplan.
Yes, that's me. So yeah, thank you all students what did so far, because this is first year of our mechatronics program. I mean, like officially first year for the senior design and capstone design. So they really work hard. I hope the next generation take some lesson from their work, and we are going to more forward for doing best. Okay. Thank you very much again, guys.
Thank you, Dr. Kaplan.
Thank you. Thank you.
Thank you,
Thank you
Dr.
so much,
Ekman.
everyone. If you don't mind, just want to remind you all, if you can do the survey, that will help us a lot and will help us also with the accreditation of the program. Thank you so much again, and thanks so much to the students. You both teams have been great, and you guys did a wonderful job. And thanks so much for everyone who joined us, and your support actually is very, very appreciated. Thank you so much. Have a good day.
Yeah, thank you so much.
Bye-bye.
Yes, sir. Thank you.
Thank you.
Thank you. Thank you for the beautiful work and presentation. Thank you all.
Thank you.
Thank you.
Thank you.